Okay, so I'll assume it's going. Let's see. And I don't know what this is. I was told this is a microphone, but I'm just going to start. So we did the erratic motion. And now I'm going to go back and forward at the same time. So we had S being the displacement, or basically the, I think it's working, so S being the displacement, and then we basically did this, and then we did this. But what I'm going to do is move into multidimensionals, in which basically you can have an X and a Y. And we'll start there, but eventually we'll move to other coordinate systems, but for right now, not. So he starts in the book with this concept that, and not with too much discussion, with this concept of a constant acceleration. But in the next section, the next chapter, you know, and you've seen this before, F is equal to ma. If this is constant, and this is constant, then that's constant. So there is just cause to actually have a constant acceleration. And if it is, you can go in and do this, and you can do this, and then you can take this and run backwards in order to get the S. So in other words, and I'll just go through that. If you took this first one, I guess I'll label this the first one and this the second one. So if you take the second one, you basically do that, and dt. The thing that happens is, and I don't think he does a good job here, but what I'll do is I'll do this, t naught, and velocity at t naught, and then I'll say velocity at t, and then I'll say t. So I'm going to be more particular than he is about doing this. And if that's constant, I can pull it out, and I can just have t minus t naught over here. Well, I could do it this way. Here, I'll do it this way. T. So that's kind of done. So actually, if I just take it out, what does that end up being? T from t naught to t, but what is that? That's nothing more than that. I'll just leave it like that for the moment. So tell me if I'm not making sense at a certain spot. I'm going to rely on you to kind of help me do that. And then you have this. Now, in the book, okay, there's something interesting that occurs. One, there's what I call a ruler and a stopwatch. And if you think about it, if you've got a problem, say, and we'll get into this by the time we're done, you can put your ruler anywhere. And if I put my ruler here, then I'm basically saying, say I put my ruler here, I got a ruler here, and I've decided that to be the initial position. And that's going to give me x at time equals 0 equals to y, oops, at time equals 0 is equal to 0. Now I could do this foolishly. You can have my coordinate system. Here's my initial position, and I'll put my ruler here. And if I do that, the initial position is not 0, it's some other location. So I can put my ruler anywhere, and I can start my stopwatch anytime. So in other words, if I sit there and I say, okay, I'm gonna have a gun, I'm gonna shoot the gun, everybody's gonna take off running, and I'm gonna shoot it, I'll wait a second, hit the stopwatch, or I'm gonna hit the stopwatch, count to 4, and then shoot the gun. That's not what they do. They basically start with this concept of, we're gonna start the stopwatch. This sounds weird. Start the stopwatch such that T naught is going to be equal to 0. Okay, if you do that, then that saves you the headache. Now, he always does that, but that's not always the case, because if you break these problems into like the erratic motion, you had this thing, we did this the other day, and here, each little region, like this region's initial time was like 10 seconds, and this one was 20, and so this region, the initial time was 10, and so you had to make up for that. So you need to be mindful that you can place your ruler anywhere, and you can place your stopwatch anywhere. And I'll get to the point where we work a problem so that makes sense in a second. So if we do that, we have this. Oh, and let me move this over. Then what he does is he says, I'm going to replace this, and he doesn't go through the process, but I'm doing it here. I'm going to call that. So the initial velocity. And so, a lot of times, it's kind of more customary to put it in front of here, and it's actually more customary to do this. And so, if you have a constant acceleration, then your velocity is just the initial velocity plus a little, this value, whatever it is, times the number of seconds that you went through. Then you can go to the next thing. So what I'll do is copy it over here and go through the next equation, because these are kind of, I'll tell you what, I'll write it at the top. Okay. So then I'm going to do another one that is this, and what we'll end up with, I'll write it down, and then we'll go through how it comes up. So these are the two equations, but give me a second and I'll show you where that second one came from. You take the first equation and you put it back here. So you had this. But then what you did is you said, hey, I'm going to put the dt over here. And then I'm going to go from S, I'm going to go ahead and keep it for right now, T0 to T. And I'm going to go from S at T0 to S at T. Keeping that, I'm being particular. I'm keeping this right now. And then I do this side, which is moderately boring in the sense that it's just this. And then over here, I'm going to take the extra step over here. Oops. T, and I'm going to put this in here. V0 plus acceleration c of t, and this is dt. So I'm taking that one that came from this first assumption, moves it through, does the two t's, and so what I end up with is v naught. Let me do it one more step over, and then I'll write it down here. Times t, I didn't write the t, sorry. Acceleration c, t squared over 2, and then I go from t0 to t. Now, technically, what this is supposed to be, now, okay, so let me, technically what it's supposed to be is this. Minus t naught, and then but here's what happens. If I simultaneously hit the gun and push the stopwatch at the same time, my initial time is always 0, then you don't get this term because this becomes 0, and that becomes 0. That's not really described in the text that well, but that's essentially what's happening. Okay, so now I'm going to move this over to here. And then I can take that and move it to the other side. And what he does is he says, well, I'll just call that s at 0. And so there you have that equation. So if you have constant accelerations, those are actually the two things you've got. Now, if that makes sense, I'm going to go back and go ahead into this where I have 2 dimensions, if y'all are okay with that. Now, it's a pretty easy jump. And so the easy jump is that I'll just copy this down. Let me get this arrow off of here. And I'll say, okay, before it was S, and believe it or not, okay, now that should actually, now he doesn't have a subscript in the book, but that actually should have a subscript as well. And this time it's X at T. So in other words, before there was a marble moving along a straight line. And this marble would move here and then move backwards, and it would always go along this straight line, and it called itself S. Now I've got X and Y. Now the marble can move anywhere in this plane. So now it's no longer S, it's X. And we'll get to a problem in a second. V x naught t plus the acceleration in the x direction that's constant, v squared over 2. But I got to have an independent one or another one for the y. And I'm writing big because of the, let me see, let me take a break for a second and see if this thing, okay, today is the 24th, right? My phone is not, okay. I don't know what's going on there. Too many things open. Hang on a second. Try it again. Oh, yeah, we're going. Okay, so here you just had this, which is nothing more than Vy naught plus the acceleration in the y direction that happens to be constant, and then y of t equal to y naught, which I said y, but I wrote v, y naught plus Vy naught t plus the acceleration in the y direction that happens to be constant, t squared over 2. So, if this all makes sense, I'll get rid of it, and we'll just go off and do a problem real quick. So again, before, this is where he started, and this is 1D. And so now, I happen to want to do a 2-dimensional problem, and so I need 2 of these. I need this one, and I need that one. So, I really don't need any of this. I'm going to redraw that differently. And so, so let's start with those. Let's go through a particular case. Let's say, and this is some stuff you've seen before. Let's say I have, well, I'll tell you what, let me not put the coordinate system on the end. Let's say we have a cannon sitting here. I'm not a good drawer, but I can draw that. Then there's a big wheel, and there's a dude back here with a stick, fire on it, and there's a thing, and it's going to shoot the cannonball. So it's going to shoot the cannonball, and of course you already know, it looks kind of something like that. And I'll just do that because I don't know where it's going to land. Now, let's say, I'm going to put my ruler right here. So essentially, when I say a ruler, I'm talking in 2D, I'm saying, I'm going to put two coordinate systems right here. I'm going to put another ruler right here. That creates my coordinate system. So if I do that, let me redo it again. If I do this, the first thing I have to identify is X naught and Y naught. And I have to identify that no matter what. So if I look at this, well, I have made my problem kind of not so fun because now I have a vector here that's maybe 5i minus 3j. So my X naught here, I'm going to start at 5, and I'm going to start Y naught at 3. Because I didn't place my ruler where I didn't use a wise decision to place my ruler. Sometimes in problems you may find it advantageous to not put it there. But let's say I want to put my ruler in a place that makes my life simpler. So I put it right here. I know this is where t is going to be equal to 0. So this is where, the guy hits the thing and hits the button and boom, the cannon goes off. So he's going to hit the stopwatch. So the key is, where is he hitting the stopwatch? Okay, so maybe he's shooting the thing, and maybe about right here, he starts hitting the stopwatch. Well, that's t is equal to 0. But that's not really conducive to solving this problem. So I'm going to put my ruler right there. If I put my ruler right there, then I have my two rulers. I have that. Okay, so the next thing I got to identify, and usually in physics it's kind of implied that gravity goes like this. I mean, you can turn your head and say this is gravity, but then, gravity this physically goes like this to me, and then I draw a coordinate, so that makes sense. So we're going to just use that. In that particular case, there's no gravity or nothing pulling this to the right, so the x, did I put the x before? Yeah. The constant x of acceleration is nothing. The constant y is the minus g. And so then you're like, okay, so it's starting to break down. Everything is going okay. Now I've got two pieces of information that I can rewrite my equations for that are right here. So what I'll do is just drop them down and rewrite them. Vx of t is equal to Vx naught. That's gone. Oh, and so that's gone too. X at t is equal to x naught plus Vx naught t, and that's gone. But we put our ruler in a location where that was gone too. So in essence, what we have is we actually have, well, we have this. This is all we've got for the x. Given that I put my ruler right where, such that, I place my ruler such that x at t equals 0, which is equal to 0, or it's kind of weird, is equal to 0. I made things really easy for myself. You can make them hard for yourself if you want. I would not suggest that, but velocity of y, which is a function of t, is equal to whatever plus this time, it's a minus because that's a minus, and so I got to replace the plus with the minus. Minus g, and then that's all that is, and then I got a t. And then I have my y, which is a function of t, is equal to now, I already had that, I placed my ruler at such that it was measuring so that that's 0, so all I have is that. And now I have my minus gt squared over 2. So now I'm like, okay, I got all the way down. Now if you stare at this, you've got two things to fill out. If I were to figure out these two, which actually these two are actually the same thing, and then this, and of course that depends on the form. So let's say we're going to use English. So I'm going to say g is equal to 32.2 feet per second squared. If I was in metric, it's 9.81 meters per second squared. But I'm just going to go with g in this right now. Generally, you can figure out meters, because meters is about a yard, a little bit more than a yard, so, you know, you get a feel for that. I mean, now the question is, what was the initial velocity? So the cannon shot out. I'm going to make my life easy. I'm going to say it's 45 degrees. And I'm going to say the velocity magnitude shooting out was maybe 100 feet per second. And that's, you know. So what that means is, okay, if you get a vector and it's 100, and you get an x component, so this is the vx, this is the vector, so this is the velocity x of that, which is 100 times cosine of 45, which is nothing more than, oh, and basically, this is the y component, is 100 times the sine of 45. That's the same thing. The cosine and the sine are the same thing. So it ends up being 100 over square root of 2. And this is 100 over square root of 2. And so you're happy because you can figure those two things out. If the angle's a little different, and we'll look at that in a minute, if the angle's a little different, then, you know, you'll have to do the cosine of whatever, you know. So what I did is, this is 45. It projects it onto this axis, the cosine, and the other one is the sine, so I don't really ever think about that much. So my equations now, let me go ahead and rewrite them. So the velocity of x as a function of time, which isn't really a function of time, but it's just 100 divided by square root of 2. And then the position, which does vary with x, is 100 over square root of 2 times t. Now there's something interesting about this, okay, and I'll talk about that in a second. Vy, which is a function of time, this time it is 100 square root of 2 minus 32.2 times how many ever seconds. And the position is 100 over square root of 2. This time there's a t, and there's minus 32.2 t squared over 2. These are parametric equations. And what do I mean by parametric? That means if I could look at the first equation. Let's look at, I got enough room down here to do it, because this is the actual look of it isn't that important. More along the lines of this. If you look at this, you get some constant, right, in that. So I'm not going to be particular about this, but this is expressed as a function of time. Now this one is a parametric as well, and I'll explain what. So now, if I'm looking at this, it has If I put in 0, I get 0. If I put in a value of, when I say 0, I say t is equal to 0, I get 0. Now, this looks more like a straight line component. Take away some quadratic component. So, in other words, if you bear with me, so this is the linear component, and I'm taking away a quadratic component. If that makes sense. So, in other words, the slope of this is this thing. Can I do the slope that way? And this distance that I'm taking away is 32.2 t squared over 2. Now, this is not the scale, but this is just to show you that x is a function of t and y is a function of t. Over here, this is not parametric. I have x and y. So what I mean is, I'm just making some stuff up. T is equal to 1 right here. Over here, t is equal to 2. And over here, maybe t is equal to 3. Oops. So I put in a value, it tells me where I'm at. Put in a value, it tells me where I'm at. So I have to put in a third value to trace this. Now, do I have to? No, actually I don't. If you put your ruler at the origin the way I did, in that the initial conditions are such that this term disappears and that term disappears, I get something really nice here. What I get is I can say t is equal to x, and I'm going to drop this for the moment. It still is there, but I'm dropping it for the moment. Okay, so here, square root of 2 t over 100. Okay. Okay, let me do that again. X, okay, wait. Okay, hang on. Let's give me a second. T, x. Okay, there we go. So, all I did is took the square root of 2, moved it over, took the 100 and put it underneath. I got that right. Now, I can do that because this term right there goes away. And by nature, in the x, on all these cannonball problems, these go away. So the only thing I'm contended with is this. If I put my ruler such that that is 0, I can end up with this. Now, I can take this and insert it right. Insert it right here and insert it right here. If I do that, now y is now a function of x because I removed the t because I put in that. Now, you'll have to bear with me for a second. 100 over square root of 2, and I'm taking the t and I'm pulling that in. X. Now I'm taking this minus 32.2 over 2 times square root of 2 x over 100, and I'm squared. So now I have a non-parametric representation. In other words, I can just write this and plot it. I can put in a value of x, and I'll get a value of y, and so on and so forth. So I actually have this plot. Looks like a parabola. Now it's not a parametric representation. It's a straight-on algebraic representation. Now, why do I do that? And I just noticed my x-axis is leaning way down there. I don't know why it bothers me. It should be more like that, but it shouldn't bother me. I guess that's because I'm moving this over to this side. So now, what is the complication that happens in this class as opposed to the complication that occurred in the non-complication that occurred in your physics? And that's why I'm going through this. In physics, they did things like, well, how far does the cannon go? How high does it go? What time did it hit the top? What time did it take till it hit the ground? Now there's many questions in this book where, okay, this was a cannon. It was shot in the football field before the Rose Bowl, but he shot it in the wrong direction. Which person did he hit with the cannonball? These are the stands. So what part of these are little people. Here's the Rose Bowl, here's the football field. So they shot the cannon, they did the wrong thing. Okay, so where does this end up? Okay, so the reason I do this is because, and maybe I should have moved that stadium back a little further, because I think I will a little bit. Let me move this, even after I drew all those people in there. Let me do it like here it is. And here's all the people, the cannonball hits this person right here. Well, why did I move it back? Well, here's why. This is an equation of y is equal to ax plus b. Okay, so over here now, I boil it down to a parabola that sits on the x and y. Now I'm saying there's a line here. There are two locations that these will cross. This is a math problem. The math problem is y is equal to constant 1 x squared plus a constant 2 x. And since it started right here, there isn't a constant 3. And this is y is equal to ax plus b. Find where they cross. In a mathematical sense, all you do is you take this, and you take that, and you say ax plus b equal to c1 x squared plus c2x. You set them equal, move them all around, and you'll have, sorry, that's a 1, c1 x squared plus c2 minus a x plus, I'm sorry, it should be a minus b equal to 0. Stare at that a minute, and what you'll realize is it's a quadratic equation. It's got this term, that term, and then a constant term. So all you're doing is you're finding two roots, two values, two x's, x1 and x2. Here's x1, here's x2, in which the path of this parabola hit across this line. That's all you're doing. You're doing nothing more than that. And so now the question is what is this A and what is this B? And for lack of a better thing to do, I'm just going to make them up, if y'all don't mind. So I'm going to say, this obviously goes back and crosses, so I'm going to make something up, and I'm going to say, I don't know, minus 20. And then I'm going to say the slope is equal to if I made it 1, it looked like this. If I made it rise over, I made it 2. So if I tilt it down, I'm going to say it's like 0.5 x minus 20. Now, often in the book, you'll see problems where you've got to figure out what that is and figure out what that is. I just made it up because I'm just going to solve the problem. That's all I'm trying to do. And I got 10 more minutes. I can kind of maybe solve that. So it wasn't any particular, it wasn't anything special about what I did there. The key is that you have to find these two. Sometimes it's pretty easy to find those two. So now I've got this parabolic equation that I want to set equal to, okay, I've already forgot what it was, 0.5 x minus 20. Now that I have all this written, I'm going to erase it and start solving below here, if you're okay with that. And if you look at this thing, what you'll see is, okay, this is an anomaly, doesn't always occur. And the only reason it does is because my cannonball angle is 45 degrees. And this cancels out, and so what I get is x minus a bunch of stuff here, which is 32.2 over 2 times that squared would be 2 times that squared. I think it's that. And then I get x squared equal to 0.5 x minus 20. So the 2's canceled. And now I guess I can move these things over there. So I can say this equal to, I'll move that over, so I get 32.2 over 10,000 x squared. Move that one over with it, and I get minus 0.5x and minus 20. So what are the roots of that thing? Y'all know? Y'all have a root equation thing, finder in there? You calculate. Or I could do, x. In math, I put a comma here. 1 or 2 is equal to minus b plus or minus square root b squared minus 4ac over 2b. But anyway, so minus b, which would be that, 3 plus 0.5 plus or minus, b squared. Did I got that right? I may have come up with a really odd one. So b squared, 0.5 squared, minus 4 times 32.2 over 10,000. Okay. And then times this one. Wait, let me think. So I gotta put in, okay, so if I put in a minus 0.5 in the squared, I still get the 0.5. But there is no b over here, but there is a c, and so then I get a plus, and then I get a 20, and I don't know what that is. So, and then I get 2, but then the b is a minus 0.5. So what did you...
It's 2a. It's over 2a.
It's over 2?
Or all over 2a. Not 2b.
Oh, is it 2a? Oh, yeah, you're right. Okay, so that's that. So that makes it bigger. Okay. I don't know what that is. But one of them's got to be minus. Well, yeah.
We got negative 32 and 188.
32 and 188. Yeah. So that would be, you go out to this guy, okay, and then this would be x equal to 188, because the minus 32 is going to be where this thing comes down and hits that back there. We don't care about that. So then that's x. Okay, so maybe I should have put this right here. So if I put in x equal 188, x would be half of 188 minus 20. That'll tell you how high he is, which actually I should have put that as y. And so half 188 is, my brain's not working. What's half of 188 minus 20? 94.
Minus 20. 74.
Oh, 74. Okay. So the dude is sitting 74 feet high in the stadium back there, and he gets hit with the cannonball. This could have been, probably would have been better that, the guy's the batter at the plate and the guy's sitting in the stadium wanting to catch it with a baseball glove. That kind of, that would have been more. So in essence, there are a lot of problems in here that all look like you had in physics. The addition is they'll have this, like they have a couple where there's a ski slope guy. He jumps off, and here there's so you've seen that where they have these big structures. I'm doing a terrible job. But when he flies off here, and then he goes, he's Olympic, and he goes way down, and he gets down there. You've seen those in the Olympics. So the question might be, where does he end up? So essentially it's a line, and it's a parabola in which the parabola actually starts here and ends up crossing down there. So that's more, this problem, and that's a classic problem. That's more along the line. This is along the lines of it hits up high. This is more along the lines of the parabola and the line are right here. Then he's got one where there's a golfer, and he's hitting up the green, onto the green, and the green is a straight line, although I haven't seen the green being a straight line, usually they're flat. So he's got that. Yes, he has one or two problems in which there's a hill. In other words, there's something that gets tossed off there, and it lands on a hill, which is a parabola this way. And the question is, where does it land? And again, you come back to the same thing. The difference is, okay, this is always going to be the same structure. This is going to be the structure of the surface you're hitting. So on that particular problem, you're going to have an x squared, ax squared plus bx plus c over here. And again, it still looks like a quadratic equation, because here you have a quadratic part, a linear part, quadratic part, linear part, constant part. Okay, so this still makes it a quadratic equation. The quadratic, the linear, and the constant, still a quadratic equation. So there's no real difference between them. So the key is, you move from a parametric representation to a non-parametric representation, which looks like this. Then you set your y's equal, and then you start solving for your x. You take your x and you go back here and put it in. But guess what? You can take your x and you can go back here and put it in. You should get the same y. Does that make sense? Because they met each other. It's just easier to put it back in the linear because there's less multiplication. And that's the only extra thing that is added to this parabolic stuff. Does that make sense? So, I initially had this room last year all set, and it was working, and I was broadcasting out of it on my tablet. I would connect it, it would do all this stuff. That didn't work. It was just such a delay, it was useless. Then I went to this, thought this was going to work. The screen is shifted off to the side. The projector sometimes, let's see if it's working today. The other day, it didn't even come on. So now, at least, they spent a lot of money on that camera. And there's two ways you should be able to get a volume. From this and from that thing. And somebody said this thing has a volume. So with all that, I should be able to get the stream going. So right now on the screen, I see the whole board, with the exception of that last little bit. Okay, well, now I see all the way on the thing, all the way right here. So it clipped this part on the screen. So I've already had a couple people who have had that COVID thing, and I don't know what the thing is about, but if you feel sick and you don't want to get somebody else sick, you'll have access to the stream. It's just, it'll be different. Well, it'll be like it used to be. It'll just be a video that's on YouTube. You go to the Blackboard, that upper thing, you click it, it'll take you to the YouTube. You can watch old things. So if you didn't get something I said today, or if you're like, I need to be reminded when you're working one of the problems, you can go look at it. You can actually speed it up to twice as fast if you wanted to. It makes me sound smarter than I am. So the other thing is, you got to go out, you got to get the book site. Well, they said on yesterday they were purging the system. Somebody, I don't know if it was in here, sent me an email that said, they talked to them and they said they're going to purge the system, so then after that, your numbers will start working. So if you got a number and it didn't work the other day, it should be working today. There are literally hundreds of people at their technical support. If you've got a number that's not working, you need to call them and say, this is where I'm supposed to be. And they'll help you figure that out. The first assignment is, I went ahead and did the one, they set up a default, which is mastering engineering, which is just like, here's how you do this, here's how you do that. Just go through that. I think no, it was due next week or something, I can move that due date around. Then the first homework is due on the 11th. The first Friday quiz is the Friday after that, which I don't know what is that, 11th and 5 days, is this 16th? I don't know, something like that. And then we're just gonna set this up. Now the other thing is, I will be probably a week or so, maybe up to 2 weeks ahead of the due date for the homework. If there is a situation where for some reason I slow down, then I can take that quiz and somehow manipulate it or do something to adjust for that. But I'm going to try to stay ahead of the quizzes so that you'll be okay with that. And that's pretty much it. I'm not going to have an in-class test till that last day, then they make us do it. And that's a rule. I've got to obey it, or they beat me with a big stick with barbed wire on it. And so I don't want to be beaten. So that's it. That's all I got. I need to figure out the microphones. So I'm going to mess around with that for a second.
Test 1, 2. Okay, so that's this microphone, Revo Labs. So apparently if I attach that to my collar and walk around, now, you know what I'm going to do? I'm going to mess with things and add a second audio stream. And I'm going to use
That, see if an echo appears. Maybe an echo will appear, maybe it won't. Okay, I'll go back.